Alright, today we're discussing vertical circles. So it's the same principle as the circles before. We're still dealing with centripetal force and centripetal acceleration. We're still going to use the same equation, F equals MAC, or mv squared over r. But in this case, our net force, our centripetal force, is going to be multiple forces because gravity is going to be involved. And so it makes our centripetal force a little more complicated, but once we can get them plugged in, the rest of the work is very similar. It's not too bad. And so they can be very complex. If we have points on the side where our centripetal force is this way, but then we also have gravity down, things get really, really messy really quick. But we're not going to deal with that. We're only going to deal with the top and the bottom of a vertical circle. And it's actually going to be quite simple. It's really not that much harder than what we did before, if at all. However, I'm not going to give you formal notes today. I'm really going to tell you how to tackle the problems because the physics is the same. So there's not really any extra formal notes to do. So what I encourage is anytime you talk about a problem with the top, draw a free body diagram. Give yourself a little picture. If we have a vertical circle and we have an object going at the top. So you can imagine if I had like a ball on a string moving in a circle and we're at the top of its motion. Okay. If I were to draw a free body diagram of this, I'll do it over here. I would have gravity pulling down. And which way is tension going? Well, tension can't push up. Tension can only pull. Like ropes can only pull, right? And so, let me turn off my screen recorder. There we go. Tension can only pull. Ropes can only pull. And so tension also has to be down. And so we end up adding these two forces together. Okay? And so whenever we do our net force is equal to mv squared over r is equal to our a, we're going to have two forces together. Now, I know last unit when I said, down is always negative, and that's what we've been doing. We're just going to go ahead and assume that whatever direction is towards the center is positive, okay? Always, in this unit, towards the center of the motion is always positive. Therefore, these two forces over here are both positive forces because they're both pointing towards the center. The reason we do that is it just makes our work easier. It's gonna be less of a pain, and so I encourage you to do that. Always make towards the center positive. And so in this case, these two forces are both positive. So we're doing T plus F of G equals mv squared over r. And in general, this is kind of an equation for any vertical circle at the top of our motion. However, of course, we may not have tension as our force always. We could have a roller coaster on a loop-de-loop like I have there, in which case we have a normal force acting. And so instead of tension plus Fg, you would write the normal force plus Fg equals mv squared over r. Essentially, we have whatever the acting force is, whatever force is doing the circular motion, plus Fg is equal to mv squared over r, and this is our equation for top of the circles. Okay. There's an important thing, though, because if I swung a ball in a circle, I may not always clear the loop. If I swing slow enough, I'm not going to make it up. I'm not going to have enough force, enough will to get all the way to the top of the circle. And so, but there is a minimum speed required, right? There's some sort of speed in which I'll clear it, but if I go any slower, I'm not going to get to the top of the loop. The string's like not going to hold or whatever. And we call that speed the critical speed, V critical, okay? And in general, that is the speed at which our applied force is equal to 0. Because if you think about the ball in the circle, if you put a ball in a circle, if it doesn't make the loop, that means there's no more tension in the rope. That rope's not doing anything else. It just kind of collapses, right? And so it's whatever our applied force is equal to 0. So essentially V crit occurs where we have this equation. Fg is equal to mv squared over r. And so that would be an important equation to write down as well. Our critical speed is going to occur there. And so a problem might be like find the critical velocity, in which case you write down this equation and then you can plug in your r, your m, and your g onto the left side. So plug in what Fg is equal to. Remember that Fg is equal to mg. And so you can go ahead and write this. Okay. That's the top of the circle. It's not really that bad. It's really just, we're just adding forces and it's still equal to ma, just like our Newton law told us. But this, since we're moving in a circle, our a is just v squared over r. Not much different than last. Now our a is just a little more complicated, but it's really not that bad. And then if we're looking for critical velocity, we just use this equation. Our applied force becomes 0 because it's not doing anything anymore. And so we just get that equation there. So let's try one. A skater of 75 kilograms tries to go through a loop of radius 2 meters. If he travels at 7 meters per second, what is the normal force provided by the loop? Okay, so we're talking about the top of the loop here. This is a bad example. I should have, whenever I created this, I should have said, what is the normal force provided by the loop? At the top. I'm pretty sure I'm more specific on the homework. Okay. So we're going to look at the normal force provided by the loop at the top. So if we look at the top, again, we have that free body diagram. We're going to have a normal force keeping us on the loop, and we're going to have gravity pulling us down at the top of our motion. So you can imagine a guy on a skateboard like that. When he's going through the loop, gravity is always pulling him down. But at the very top, if he's going fast enough, he's still kind of pressed into the wall, which means the wall is pushing back and providing a normal force downwards. Normal force is not always up. Sometimes it's down. It's just always the opposite direction of the surface. And so then, if we rewrite our Newton law, F equals ma, we know the sum of the forces, the normal force plus Fg, is equal to m times a. But what is a? We remember that for this unit, our a is equal to v squared over r. So we're just going to write that instead. And again, we have this equation that I showed you last time. The normal force plus Fg is equal to mv squared over r. All right. And we're looking for the normal force. So we're looking for F of n. Let's plug in everything else. Fn plus mg equals m v squared over r. What is mass? Mass is 75 times 9.8 is equal to 75 times 7 squared over 2. And I'm going to have to type this into Google because I don't have my calculator on me today, unfortunately. I'm at home. 75. So 75 times 49 divided by 2. And then 75 times 9.8. So this is equal to 1837.5. 75 times 9.8. This is 60. And so the normal force should just be what, 1777.5 if we subtract 60. Easy enough. So now the question is, what is the slowest I could travel and still clear the loop? This is my critical velocity. Imagine if you barely clear this, you barely clear the top. If you're barely clearing it, the wall's not really doing much. You're essentially just floating in the air. This normal force stops acting on you. It becomes 0. So again, we have this equation. If we want to find the critical velocity, we're essentially looking for where mg is equal to mv squared over r. Now, some people who understand their algebra a little bit, if I have an m multiplied by both sides, I can actually cancel this and make the equation a lot simpler. G is just equal to v squared over r. And if I solve for v, I'm just going to multiply both sides by r, and you get that v squared equals g times r, or that v is equal to the square root of g times r. And this is something a joke we make. Our critical velocity is very much often just the square root of gr at the top of a loop. And so I'm just going to do 9.8 times my radius, which is 2 meters. And then I'm going to take the square root of that number, 19.6. and get an answer of 4.43 meters per second. And that's my critical velocity. All right, the other point I want to talk about is the bottom of a circle. Okay, at the bottom of a circle, now our surface is this way. So our normal force acts up, but we still have gravity down. So now we have the same sum of the forces equals ma, but instead, at the bottom of a circle, we're going to have our applied force, whatever it is, if it's normal, if it's a ball and a string acting in a circle, so it could be tension. It's our whatever applied force is minus Fg is equal to mv squared over r. And this is the equation you should have down for the bottom of a circle. Whatever your applied force is, whether it's normal or tension or whatever is doing the force, goes here, and then minus Fg equals mv squared over r. Because if we were to draw a free body diagram, we'd have Fg down and whatever applied force is keeping us going in a loop. Now, if you think about it, that means our applied force has to work extra hard because before gravity was helping it pull back down, so it was a little bit lighter. But now that we're at the bottom of a loop, that's where we're heaviest. That's where we're pushing down the most. And so F1 has to work extra hard. And so we don't really have a critical velocity that like we can't clear the bottom, because of course we can clear the bottom. No matter what we're doing, we're at the bottom. We're always going to be gaining velocity as we go down, right? Think about a roller coaster. No matter what, we're going to be gaining more speed the more down we go. But what could happen is if we have a ball and a string, if tension is too great, if this string can only, withstand like 500 newtons, and we go too fast, this rope's going to snap. And so we have a different critical velocity. We have a critical velocity so that the rope can't handle. So the critical velocity at the bottom is essentially just solving for F1 though. It's really not as complicated as the other one where we had to like let F1 be 0 and we had to think about it. This one, I'm probably gonna say, the rope can't handle more than 500 newtons. And so all you're really doing is plugging in 500 newtons into that equation. But if you want a more formal way, our critical velocity is just so that F1 is equal to Fg plus mv squared over r, and this is our max force. The max force, this thing can withstand. And then you just plug in numbers and solve for v, or you're solving for the max force. It might give you the critical velocity. There's really not a special equation here like there was on the last one. You're really just plugging in whatever F is, or you're solving for F if you're looking for it, whatever the max force is. So let's see what that looks like. So pendulum has a mass of 90 kilograms and has a string with length 5 meters. So that'll be our radius, and here's our mass. The pendulum is dropped and reaches a velocity of that, so that's our V. What is the tension of the string? So we're looking for tension first, and then the string can support a maximum of 1600 newtons. What's the max velocity it can support? Okay, so we have two different questions here. To start with the first, what's the tension? And so again, we're gonna have that equation. Our applied force minus Fg is equal to mv squared over r. In this case, our applied force is tension, and that's what we're looking for. We're looking for what is a tension. We know our mass is 90, and our g is 9.8, because I'm plugging in Fg equals mg. Again, our mass is 90. V squared is 2 squared over our length of 5. And so I'm going to plug that in. 90 times 4 divided by 5. I get 72 over here. And then 90 times 9.8, 882. And so we add them together because we're going to add that 882 to the other side to get our tension. So tension is equal to 954. Again, it's not complicated. And then if we want to find a string that can support a maximum of 600 newtons, we're using the same equation. The bottom's a little easier. We only have one equation for the bottom. But in this case, our tension can only withstand 1,600 newtons. So our applied force is only 1,600 newtons. Our weight is the same, right? We should have the same number here. Our mass didn't change, and so G didn't change. And so we're really just looking for V now. And so let's go ahead and simplify the left side. 1,600 minus 882, 718. And depending on how you like to do your algebra, I like to simplify the right side, but I'll go ahead and do, I think, what makes most sense, multiply by 5 and get rid of it. But personally, I would probably do the 90 divided by 5, if you know what I'm talking about. I think that's a little easier to do, but I think this makes more sense visually. So we multiply both sides by that, and they cancel, and we're left with 90v squared. Then that means I need to divide by 90 now. So I get 40. I'll go ahead and show it. 39.9 is technically what it is. And then we take the square root of that answer. And we get that V is equal to 6.31. And so that is the fastest we can go without breaking the string. So that is our max velocity. If we go any faster than that, then this becomes too big, and the net force that we can't handle that net force. And with that, that's where we're going to end today. Next time, we're going to do some special problems, basically very specific problems. Almost every single situation has its own slightly different equation, but honestly, for the most part, they work the same. And so it's really not that hard of a unit, as long as you have, especially if you can use notes on tests, which I'm allowing notes on tests. And so when you use your notes on tests, really this unit's not hard at all. I would just encourage, as we progress with notes, have one special page is written out like, here is my vertical circle equations, boom, boom, top, bottom. Organize your notes. And I suggest that doing for any math class or any physics class. After you've done all your notes, organize them. It's going to make doing problems a lot easier and studying a lot easier. And then you review your notes while doing that. And so it's very beneficial to organize notes after you've taken them. With that, you should have your homework assignment up, and I'll let you get started. Have a good day.